In this third installment of the Ghost lectures, we give the perturbation theorem, for general matrices, and then secondly, we specialize this to the case of Hermitian matrices. Again, one of the difficulties for the general case is that we need to be sure that A plus E has an invariant subspace, and that's why we need to do some extra work. So A plus E being a perturbation. We can come up with some examples where if you start with something that has some low-dimensional invariant subspace, a small perturbation of it may not have an invariant subspace. But this cannot happen for Hermitian matrices. So this is easier, as we'll see, because we do not need to check if there exists an invariant subspace. So we'll get to that. So let's give our the main perturbation theorem. Suppose, as before, that we have a matrix A, and we have an orthonormal basis, x1 expanded by y2, and now I'm going to assume that x1 defines an invariant subspace. So x is equal to r of the range of x1 is A invariant. What it means, of course, for this to be A invariant, as we've seen, is that x1, y2, A, x1, y2 is equal to L1, something up here, which I'll denote as before H, L2, and the key thing we saw at the beginning of the first of these ghost lectures is that this has to be a 0. So this is the implication of invariance. Is equivalent to that being a 0. So what happens once we add a perturbation? So suppose that we add a perturbation E. A plus E, where E in the same basis is just going to be E11, E12, E21, E22. So what I want to know is, does A plus E have, or I should say when, does A plus E have an invariant subspace that is close to the range of x1, and how close? So that's what we'd like to answer. So we can try to directly use the approximation theorem that we just proved at the end of the last lecture. So we know that by assumption that A plus E in this basis is equal to L1 plus E11, H plus E12, L2 plus E22, and E21. So in terms of our previous theorem, this plays the role of what we had before was G, and this is what was H in the previous theorem. So applying that directly, we have the following. This is what we would like to say. So from our approximation theorem, let's let for now our consistent norm. Remember that the approximation theorem holds for any consistent norm. and the operator norm is an instance of that. So just to be specific, let's take that. And now let's define quantities gamma and eta and delta as we had before. So what was gamma, but I'll put a little tilde on them because in this case they represent perturbation. So what was gamma? Gamma was the norm of G in the approximation theorem. So the norm of G in this case, the role of that is played by E. What was eta? Eta was the norm of H, what appeared in the upper right-hand corner. Now instead of H, we have H plus E12. So this is not very nice here because we're talking about perturbations, and I don't want to know about H. H is not a perturbation. H is part of my matrix A, but I don't want to have anything that depends on the specific structure of the perturbation other than its size. But it's easy just using triangle inequality to bound this by the norm of H plus the norm of E12. So this is actually the bound that I'll use for eta tilde. And what's delta? Delta is going to be the separation, sep, between the blocks on the diagonal. So in the past it was L1 and L2, but now we have L1 plus E11, L2 plus E22. So if we apply the theorem directly, what does this tell us? So the theorem then promises that if, and this is the condition that we need to know that there exists an invariant subspace, if gamma tilde eta tilde over delta tilde squared is less than 1/4, then there exists an invariant subspace of A plus E. And in particular, there exists that matrix P, which, if you recall, was used to actually construct that invariant matrix. And moreover, that P had a bound on its norm, in this case, its operator norm, less than twice gamma tilde over delta tilde. And so one implication of this is, as we saw when discussing how to use the approximation theorem, in particular, this implies that if we look at the largest canonical angle between the two subspaces, its tangent is bounded by the norm of P2, which is equal to twice gamma over delta. So this is an immediate consequence of the previous theorem. Now, so the proof of this is essentially immediate. There's really nothing to say. It's just but there's something unsatisfactory here. Again, what is it? Let's look at our three quantities. So let's look at gamma, eta, and delta. And so what we'd like for gamma, eta, and delta is for them to either depend on properties of A or on the magnitude of E. What is not great is for gamma or eta or delta to depend on the specific structure of E. And again, what's the reason? Because typically when you're thinking about perturbation, you only have a guarantee on the size of the perturbation. It's much more rare, or it would lead to much more specific theorems if we had results if our theorems depended on specific structure of E. So of these three quantities, what satisfies that? So gamma is equal to gamma tilde is equal to just the norm of E21. So that's good. Eta tilde, now we defined it in terms of the norm of H plus the norm of E21. So that's good. So basically the last offending thing here is delta, because delta is the separation between L1 plus E11 and L2 plus E22. So while the theorem, of course, still holds, this expression is not ideal. So we need to fix that. So again, the issue is that the results we just gave depend on this quantity, delta tilde, which I defined as separation of L1 plus E11, L2 plus E22, but would ideally we want some quantity delta tilde that depends on A. So in other words, it's allowed to depend specifically on L1 and L2, and on the size of E. So in other words, something like the magnitude of E11 and the magnitude of E22. So this is really the only missing piece to having a usable theorem. And it turns out that we have that. Okay, so we need to understand. The point is that we need to better understand set. And it turns out that there's a continuity result. That's exactly what we need, and actually follows quite easily just from some multiplicative property of consistent norms and triangle inequality. So we need the following continuity theorem. More than a continuity theorem, it tells us that it's Lipschitz continuous with Lipschitz constant 1. It simply says that the quantity is bounded below by separation of Lm minus E minus F, and it's bounded above by separation of Lm plus E plus F. And this is true for any consistent norm. Okay, and this is now finally what we want, because sep Lm and in the lower bound and the upper bound are allowed to depend specifically on properties of A. For us, that would be separation of L1 and L2. And E and F, now this just depends on norms. So the proof of this is, I'll leave it as an exercise, and it's not difficult. It's not difficult at all. So what do we get? So let's put that. Let's rewrite the previous theorem. So if x1, y2 again is a unitary matrix, and we have this picture. Again, this 0 exactly means that the range of x1 is A invariant. If we have E is a perturbation with x1, y2, E, x1, y2 equal to E11, E12, E21, E22, then if we write gamma tilde, the norm of E21, eta tilde is the norm of H plus the norm of E12, and delta tilde is equal to sep of L1 and L2 minus E11 plus E22. So this is the difference from what we had before. Then the conclusion that we had written before holds. If gamma tilde, eta tilde divided by delta tilde squared is less than 1/4, there exists an A invariant. Oops, not A invariant. There exists A plus E invariant subspace such that its largest singular, the largest angle between the new invariance of the A plus E invariant subspace and our original A invariant subspace is bounded by twice gamma tilde over delta tilde. In particular, there are a bunch of other things that I didn't write down, such as what actually is the invariant subspace. But this is now just a direct application of the approximation theorem. So, a kind of high-level summary here is that these perturbation guarantees depend essentially on two things, and one of these is the size of the perturbation, and that's obvious that it should depend on that. And then the other is that it depends on the matrix, the original matrix A being perturbed, and really what we're talking about is the original invariant subspace. And it depends on those through this quantity, the separation of L1 and L2. And let's remember what that is. So recall that we defined the operator T as the operator that maps the matrix X to L1X minus X L2. And recall that we've seen various properties of it, namely if this T is non-singular as long as L1 and L2 have disjoint spectrum. And recall that we had defined the separation to be this measure of how far apart L1 and L2 are measured through T. So this was the definition of the separation of L1 and L2. And a final theorem that I'll give before moving on to permission matrices is a bound on this. That's a little bit more easy to handle intuitively. And this is that for any square matrices, L1 and L2, then and for any consistent norm, then again this is what SEP is defined as. It's bounded by the smallest eigenvalue in their difference. So again, we've seen this before. This is a set that is the Minkowski sum of or Minkowski difference of the two sets, the set of eigenvalues of L1 and the set of eigenvalues of L2. So we'll give the proof here. So we know that if this is equal to 0, that's equivalent to saying that t is singular, and we also know what the eigenvalues of t are. Namely, they're exactly given by that Minkowski difference. So that's equivalent to saying that these have some overlap, and therefore the min on the right-hand side would be equal to 0. Now, if this is strictly positive, it means that t is non-singular, and thus has an inverse. And something that you should check is that this is equal to the supremum now over q equal to 1, t inverse of q, which is just the largest, which is just the induced norm on the inverse of t. It's the first exercise. The second exercise is that for any consistent norm, the spectral radius of a matrix is bounded by the norm on that matrix. So this is easiest to think about in terms of the operator norm, which we know is consistent. So the spectral radius of any matrix is bounded by the norm of that matrix, as long as this norm is a consistent norm. So in particular, what this exercise gives us is that the spectral radius of T inverse is bounded by this norm of T inverse. And recall that we had also shown that the spectrum of T is just equal to this difference of the spectrum of L1 and L2. And therefore, what this tells us is that 1 over the separation of L1 and L2, which we said by the first exercise above is equal to the norm here, this is greater than or equal to, by consistency of the norm in the exercise above, the spectral radius of T inverse. But the spectral radius of T inverse, we know what the spectrum of T is, so this is exactly equal to the max of and this is what we wanted to show. So what does this tell us? This says that if L1 and L2 have eigenvalues that are close, then this tells us that the separation is small, which tells us that 1 over delta is big, which tells us that the bound on the perturbation is not going to be good. And that doesn't mean that a particular perturbation wouldn't result in just a very small movement. But the best we can get by these bounds is something that big. So this is a kind of necessary condition that in order for these bounds to be useful, we need the eigenvalues of L1 and L2 to be far apart. But that's not enough for non-Hermitian matrices. So for Hermitian matrices, we will see that the condition that the eigenvalues of L1 and L2 are far apart is not only necessary, but it's also sufficient for a good perturbation bound. So is necessary Necessary is what we just proved in the previous theorem, but it's also sufficient to guarantee stability. But it's not true in this case. So here's a following exercise which shows that. So this exercise shows that for non-Hermitian, it's possible for the separation of L1 and L2 to be small. Again, small is not what we want. We want it to be big. But to have the eigenvalues of L1 and L2 be well separated. So as a concrete exercise, compute the separation of L1 and L2 and the min of L1 minus L2 for L1 equal to 0, 1, 0, 0, and L2 equal to 0, 1, epsilon 0. We're going to close this lecture now, and in the next Ghost lecture, talk about Hermitian matrices.